Okay, so two things that we're going to talk about in this section. First is directional derivatives. Second is gradients. So far, if we have a function in 3 space and we have a graph that represents z equals f of x, y, we can do two things so far. If we have a point corresponding to x naught, y naught, and we map that up to the surface, we can find instantaneous rates of change in two directions. We could find parallel to the x-axis, we could find a slope of this tangent line, which would be partial z partial x. And we could also go parallel to the y-axis, find this tangent line here, and that would be partial z partial y. So far, those are the only two things that we can do with partial derivatives. Okay, so now the question this unit, or this section, in real-world applications, let's say this is actually a surface or a valley or a hill or what have you, and you're standing right here. Well, there's more than two directions that you can travel, obviously, right? You're not going to be confined to just go either up, down, or left, right. I mean, you can go any which way. So maybe you're interested in going this way. So now we have another slice of the surface, and maybe you want to know what the instantaneous rate of change is in this direction. Okay. So now, to do that, what we'll do is we'll use a vector, particularly a unit vector, to describe the direction that we're going to look at. Okay, so u is going to be the direction and since it's a unit vector, it'll be u1i plus u2j. And now the line determined by u can always be found by using the arc length parameterization. This is from a while back. You just do x naught plus su1, and then y equals y naught plus su2, if this is the parametric equation. Okay, so obviously this now will be an arbitrary vector which can represent any possible direction. So that'll give us the freedom to say, well, what if I want this direction? What's the slope if I go that way? What's the slope if you go this way? And so on and so forth. Okay. And so now just to review, for s equals 0, so if this is 0, then we're talking about xy actually equaling x naught, y naught. Okay? As s increases, xy moves in the direction of the vector u. Okay? So these are just some conditions that we are assigning to this. So now if we're interested in dz ds, at s equals 0. Okay, this is going to give us the instantaneous rate of change of the function z equals f of x, y with respect to the distance from x naught, y naught. So for this tangent line up here, which now I'll do in black, we have our reference vector in 2 dimensions, which is u, right here. If I take the derivative of the length traveled, or find the rate of change as we get really, really close to this initial point, then what we're arguing is that that, in fact, will be the instantaneous rate of change in any given direction. Okay? Which hopefully makes some sense intuitively. Okay? So now here's the definition. Given f of x, y, and then a direction, u equals u1, u2, which is a unit vector, then what we call the directional derivative of f in the direction of u at the initial point x naught, y naught is notated as du, where u is a little subscript of f of x naught, y naught, and it's defined by doing this calculation up here that we sort of intuitively gathered, that if we are interested in a slope in any particular direction, we can have a reference vector, think of the tangent line, and then take the instantaneous rate of change of ds, or I'm sorry, not ds, but dz ds, so that we get the difference in height with respect to how much we've traveled along this tangent line. Okay? So to do that, the calculation is exactly dds. You plug in the parameter x naught plus su1, y plus su2, but we want this s to be so small that we're actually going to evaluate this when s is 0. Okay, so that's what we're trying to do. And just to clarify, so that we don't have all these different directions, here's what we're doing again. So we have a surface. We have some line which can be defined in terms of its arc length parameter. And on this line, we have a unit vector as the reference vector. And what we're doing is mapping this up to the surface, so that now when you slice the surface, you get a slope in the direction of u. At this particular point. So this is what we're doing. So first we think two-dimensionally. We talk about a line. We have a arc length parameter definition for it. We use that and plug it into the surface, and then we take the derivative with respect to s as s goes to 0, and then we have our instantaneous rate of change. Sounds like a lot. It's not too bad, but there will be an easier way. But this is how we need to start so that we actually understand the shortcut that we're going to do in a little bit. So here's an example. let's say f of xy equals the function x times y. And we want to find and interpret the directional derivative at the point 1, 2 for the direction root 3 over 2, 1/2.
What does that thing say over there?
Where?
D? Oh, is that D?
Yeah, sorry. Capital D sub u, directional derivative of 1, 2. The direction assigned is root 3 over 2, 1/2. That's our unit vector. Okay, so now using the definition, here's what the calculation looks like. We say du of 1, 2 will be d ds. I plug in the direction into my function. So we do, since the initial point is 1, we do 1 plus root 3 over 2s, 2 plus 1/2 s, and then eventually we plug in 0, but we're going to first plug in and then take the derivative. So let's evaluate if I replace x with 1 plus root 3 over 2s and then replace y with 2 plus 1/2 s. So then that's going to be d ds of 1 plus root 3 over 2s times 2 plus 1/2 s. We're still going to do s equals 0 eventually. Multiply that out. We get 2 plus, middle terms have an s in common, and it would just be 1/2 plus root 3 of them. And then last term will be root 3 over 4 s squared. So after you expand that, here's where we're at. We can take the derivative. So then this becomes, with respect to s, 2 goes away. With respect to s, we get 1/2 plus root 3. Plus, with respect to s, this is going to be root 3 over 2 s, evaluated when s is 0. And then now we plug in 0. So then this last term goes away. Our exact rate of change is 1/2 plus root 3, which is approximately 0.5, 1.73, so 2.23. I'm doing that because we're supposed to interpret what this means. So what this means then is that our function, whatever xy looks like, so here we are, for every unit that you travel in the direction of u, so maybe we should write this down. For every unit traveled in u direction, what happens to f of xy? Increases by, good, 2.23. Locally, of course. Okay. For 3 variable, oh, yes.
So what happened to the f again?
Back here?
Yeah.
So this, I'm actually plugging into x and y.
Oh, okay.
So since now we're basically plugging in that direction, that line direction in the function so we can see what's going on. X is going to be 1 plus root 3 over 2s.
Okay.
Y is 2 plus 1/2 s, and then we're just now we just multiply them out. Does that make sense?
Yeah.
Okay. Any other questions? In 3 variables, it's the same thing. You'd have DDS, you have f of x, y, and then a z term. It's the same concept, so I'm not going to waste the time doing an example with that. And Instead, I do want to get to this, though. A more convenient way to find directional derivatives. So it's actually going to be a theorem, and maybe we'll prove it.
Maybe it'll be on the test.
Maybe. It's an easy proof. So let's say f of xy is given. I'm kind of being brief here. And then the direction, u1, u2, that's given. That's a unit vector. The theorem says that the directional derivative of f at a particular point, x0, y0, is simply going to be partial x evaluated at that point times u1 plus partial y evaluated at that point times u2. Here's the proof. We start with the definitions, or basically what we know we can do. So if z is going to be a composition of functions, just like we've been doing, x0 plus su1, y0 plus su2, with x of s equaling x0 plus su1, and then y of s, so we're defining exactly what everything is here. Then, by definition, the directional derivative at a particular point can be calculated by doing the derivative with respect to arc length of whatever function we have. So basically this, when you plug in these parameters. Which I'm going to write as, since this is actually z, dz ds, evaluated at s equals 0. And now this is, again, I think it was Bouvin that asked, well, if it's easier to plug in the compositions and find the derivatives directly, why must we do the chain rule? Here's another application of where the chain rule is going to save us. By the chain rule, what is dz ds going to be? Partial z partial x times dx ds, good, plus partial z partial y dy ds, evaluated when s equals 0. Well, partial z partial x is just another way of saying essentially this, right? F of x naught, or partial x of x naught y naught. And now, what's dx ds going to be? Looking back at x. u1. Now the reason I'm using x naught, y naught, when you plug in 0, you understand that we're going to be exactly at that point, right? So we're going to get exactly partial y, x naught, y naught U2. So pretty easy to prove. Okay. So real quick, back to the first example. We had f of xy was xy. We wanted to find du at the point 1, 2 in the direction of u equal to 3/2, oh not 3/2, root 3 over 2 and 1/2. Well, now with this new formula that we've proved, we just do partial x, which is y, times u1, which is root 3 over 2, plus partial y, which is x, times a half. Of course it's way better. And then plug in the point now. What do we get? If y is 2, then we get root 3 plus x is 1, 1/2. Oh, so much nicer. Thank you, chain rule. I'll see you guys tomorrow.